Welcome back to ECE 442-542. If you're paying attention closely, you're seeing that this particular lecture is a second attempt to what was presented earlier tonight, and unfortunately the audio was terrible on that video recording, and so I'm hoping that this time around we'll have a little bit more success, but you can be the judge of that. What I want to do first is say that homework number 7 is due on Saturday, and it's due at 11:59, but we want homework 7, and that will be the last required homework assignment. We will have a homework number 8, which will be discussing topics from state space design approaches, and that will be Unit 8's topic. ECE 542 students have their project due a week from Wednesday on the 3rd of May, which is the last class day of the semester, and that's also when our teacher course evaluations are due, which you can access at this link, or I'm sure that you've had emails reminding you that you need to complete your TCE forms. Those I really would appreciate you filling those out. That gives me some clues, some tips, some insight into how I can change the class to make it better for the next time that I teach it. The final exam, as a reminder, is on the last day of finals, which is Thursday, the 11th of May, and that will be from 1 to 3 p.m. in this classroom. Today, what I want to do is wrap up the transfer function controller design approach, and we've been recently talking about the PID controller. We'll go ahead and illustrate some Matlab commands, rltool, rlocus, and rlocus find, that will help us in that process of designing PID controllers, where we have the two flexible zeros that we can select, those being either real or complex conjugates, and then adjusting the gain, K, to locate our closed loop poles on the appropriate spot or spots on the root locus branches. After we finish with the PID controller, we'll still stay with transfer function based design, but we'll talk about general controller design with the root locus, and by that I mean now we have a way, or we still have our zero shaker and our pole shaker, and we want to be able to sprinkle the appropriate poles and zeros on the z-plane for the possibility of the case where we might have an unstable system, or we might have a system that has zeros outside the unit circle, which are also called non-minimum phase systems. All of that will then finish up our transfer function controller design, which we will go ahead and say that's enough for today's lecture, but Unit 8, which will be the remaining topic for this semester, will be dealing with state space controller design. We'll now jump back into modeling our systems via a state space representation and illustrate the different design flexibility that we have when we represent our system as a state space based controller. What I want to do now is wrap up the PID controller design. And for this PID controller design, we have our conventional block diagram with our plant G of Z, our PID controller, which we're labeling as capital C of Z. And that now, when we have a PID controller, that immediately tells us that we have a pole at the origin and a pole at z equal to 1. The pole at z equal to 1 gives us a type 1 system if we don't have any poles there already in our plant, and that type 1 system now allows us to achieve zero steady state error due to constant inputs, reference inputs at R of z. But as you can see in this PID controller, and like we talked about in the last lecture where we developed this structure, the flexible parameters in this controller design are in the numerator expression. We can select beta 1 and beta 2. Those are our two zeros. Those zeros could be either real or they could be complex conjugates of each other. And we then have the gain k bar to select once we've positioned our zeros beta 1 and beta sub 2. Let's illustrate this or remind ourselves of what we can do with a PID controller for this particular system, g of z, which is 1 over z minus 2. In this particular case, I hope it's clear that we're starting with an unstable system, and if we are going to actually control this with a PID controller, then we know immediately that we're putting one pole at z equal to 1, and we're forced to put the second pole of our PID controller at the origin, and that's in the denominator of our capital C of z. What we don't know is where to locate our zeros, beta 1 and beta 2, and once we've picked those, then how do we select the gain k? Well, we select the gain k to hopefully achieve all of our branches of the root locus, and in this case, we have 3 now open loop poles being the poles of g of z and our controller c of z. That will give rise to 3 root locus branches or 3 closed loop poles, and we want all 3 of those branches for a given value of gain k or k bar to be inside the unit circle. Now, if we were simply guessing at where we might locate some zeros, if somebody actually decided to put one of their betas at that location, then I hope it's clear that no matter what we do, we're stuck with a branch of the root locus living between z equal 2 and that 0 location. And that then means that we probably want to refrain from a 0, one of the betas, between 1 and 2. A more appropriate place might be if we actually, in a sense, canceled this 0 at the origin, then we would be back to the PI controller that we have seen before. But in this case, what we want to do, let's say that we now offset those a little bit, so we now have a beta 1 and beta 2 if we assume that those are real. Now we can think about what we have for a root locus diagram. We have a branch, in fact 2 branches between 1 and 2. Those come together. We have 2 branches between the 2 zeros, and we have a third segment of our root locus diagram that actually goes off to minus infinity. The branches between 1 and 2, they can't just stay on that real axis segment. They will break away, and they will actually approach the 2 finite zeros, and the pole 0 excess being 1 will now give us a asymptote 1 infinite 0, and that infinite 0 as it is at an asymptote of minus 180 degrees. And I hope it's clear that we will be trying to generate maybe closed loop poles. The idea then is to get 3 closed loop poles. There's 2 of our closed loop poles, and we hope that the third pole stays inside the unit circle, and that will be for a particular value, which I'm going to maybe in today's class be calling the Goldilocks value of our gain k bar, but we will be having a smaller value of gain k that will produce a stable system, meaning what's the gain to get us right at the boundary of our unit circle and still keep that third pole on the negative real line inside the unit circle. And finally then, while those 2 poles are marching off to the finite zeros at beta 1 and beta 2 as we increase the gain, this third pole will zip out of the unit circle, so we are bound by that maximum value of gain k, and our range of stability then for this system would be then determined if these squares and stars are in the manner shown, then we would have a lower bound on our gain being the gain to get us to the squared location in the z-plane, and the starred value of gain would be the upper limit. And what we're wanting to do is try to find a Goldilocks location between those extremes, which I've now indicated by the triangles, to give us the behavior that we want. With this PID controller, here's maybe the strategy that we want to think about, and that is to go ahead and select beta 1 and beta 2 to give us a stable closed loop system, and then manipulate those in a way that we will then achieve a more acceptable closed loop behavior. And we'll illustrate that hopefully in just a little bit through the use of Matlab and some of the commands in Matlab. To get us started on this idea of starting with a stable controller, in the last lecture we actually designed a PI controller, not a PID controller, but a PI controller that would stabilize that system. And the PI controller that we designed, it obviously has a pole at z equal to 1, but we found the 0 location using the phase angle condition, and that 0 location ended up being at 0.9833, quite close to the pole at z equal to 1, but that gave us then our what we were at the time saying, let's see if we can design a controller that would put closed loop poles at 0.9 plus and minus j 0.1. And in fact, C sub 1 of S will do that. If that's now already been done, maybe a PID controller could use that somewhat as a base or as a starting location. And so you might be interested in asking, when is this PID controller equivalent to C sub 1 of z? And if you think about that for just a little bit, hopefully you can see that if we forced one of those betas, beta 1 or beta sub 2, to be 0, then in fact we would have a z factor in the numerator that would cancel the pole at the origin in the C sub 2 of z expression. And doing that, so when is C sub 2 of z equal to C sub 1 of z? Well, that will happen when beta 1, let's say, is equal to 0, and beta sub 2, now if we let that equal 0.9833, now we have the numerators matched other than the gain, and if we select the gain, k bar, to be 1.2002, then in fact we can have the PID controller equal to the PI controller. And so it might be nice to use that as sort of a first cut at a PID controller and then move away from that and see if we can achieve a more acceptable closed loop performance using a PID controller versus a PI controller. And to do that, let's go ahead then and use Matlab, and in particular I want to look at rltool, which is a function in Matlab, and we'll use that to show how to maybe more effectively adjust the parameters in the PID controller to produce a more acceptable closed loop set of values. With that said, then let's go into Matlab, and I now have created a diary file that I hope I will be able to then share with you in the form of maybe inside these notes. And first, let's just, for starters, let's go ahead and design or define our unstable plant that we are working with in this particular example. And it had a 1 for the numerator expression. The denominator had a single pole at 2, and we're not really specifying the sampling period, and so here is now our unstable plant or the unstable system in this example. Matlab will now know that it's a discrete time system because we gave it that third argument in the function, and in fact we gave that third argument to be a value of -1, which says we're not specifying the sample time, but if we don't, we still have a pole at z equal to 2. We can also say, let's go ahead and introduce our PI controller, but in fact, let's introduce that PI controller without a gain associated with it. And we'll see that we can then adjust the gain using the tool, our rltool or root locus tool, in just a minute. But here we now have our zero factor, which is z minus 0.9833. We have our pole factor, which is z minus 1, and we have again an unspecified sample period, but this is now our PI controller without a gain. And to illustrate what can be helpful or useful in designing controllers, not just PID controllers, but let's look at this function in Matlab called rltool, and the version of Matlab that I'm running now is a little dated, and so the way that rltool looks in this versus a more recent version of Matlab is not that consistent, and so I don't want to spend a lot of time on the interface, but I do want to give you a feel for how you can maybe use rltool in a control law setting or in a design setting. I'll say I don't want to look at any help right now, and in fact I issued rltool without any arguments, so it doesn't have a system incorporated in it, but I can actually introduce that system data based on what I have already input into the Matlab environment. I have working in my workspace, I have my system G, which is a 1-by-1 transfer function or single input, single output, and I have my PI controller that I labeled C sub 1. In this block diagram, I hope it's clear that H and F, for now, we'll just leave those as 1. We're not going to upset those at all, and we do have this unity output feedback with, and it's assumed to have a negative feedback in the default setting, and our plant is G and our controller is C. We can actually tell G to actually be the little lowercase g that we input already into the workspace by highlighting G, browsing among the variables in Matlab, and let's find G and import that. And now we close that particular import operation, and now we've converted or set the system G in this block diagram to be our system, unstable system, lowercase g. We can also do the same with our PI controller, which we now have used or labeled as C sub 1. We import that, and now we have our system in this tool, rltool, defined. We have our PI controller and we have our plant. Let's go ahead and look at the graphical tuning of this. So in plot number 1, which we want to show, we're saying let's look at the root locus and let's show that design plot. And this is the root locus diagram that we would have expected. You can see that in the appropriate gain, or with the appropriate gain value, it's actually unstable. But if we now rotate those magenta squares, those are representative of the closed loop poles, and if we put those at 0.9 plus and minus j.1, we have now a gain value, maybe that's specified, of 0.0198 to get us to that location for the appropriate values that we had for G and C sub 1. But the nice feature relative to this is that we can not only look at moving those closed loop poles, but as we're moving those, we could actually look at how those are impacting the closed loop step response between the reference input R and the output Y. So let's show that plot also. I thought I clicked. So there is the step response for those closed loop poles that I've now indicated. So we have quite a bit of overshoot, but because of the PI controller, we will settle to a steady state value of 1. Our settling time is quite large. It's about 60 samples. We really didn't specify the sample period, but you can see now if I adjust my gain of my system, or which effectively now changes the closed loop poles, I can now modify this dynamic behavior, the closed loop step response. And that's a nice feature of this particular tool, which is rltool. And what we can also do is, in this particular compensator design, we can now introduce more poles and zeros. We can add a real pole. We could add complex poles. That's showing that one's in the upper half and one's in the bottom half. We can add a real zero, and we can add a complex pair or complex conjugate pair of zeros. Let's go ahead and convert this now into a PID controller by adding a pole, and we know that that is fixed and will be right at the origin. Hopefully that's where that's at now, and you can see that if we don't do anything more, this is going to produce an unstable system. We have our two branches that are outside the unit circle. This isn't going to work the way it's designed right now. So we might want to enter it, and you can see then in the step response that it's obviously going unbounded. But the PID controller not only has the two poles, and those are fixed, one's at the origin and one's at 1, but we also have two zeros. Let's just assume that we have that zero fixed at 0.9833 and put another zero in. And now you can see that we have changed our dynamic behavior. We have a stable system, and all of these magenta circles, we now have 3 closed loop poles. The 2 poles branches between 1 and 2 meet, they circle around again because we had that 0 at 0.9833, and for this particular choice of gain, we still have this pole inside the unit circle and our 2 complex conjugate poles. Now, ideally, if I could grab that 0, which I was able to do, I can now move that around, and maybe now if I move that to, let's just say that let's move that to 0.9, and let's move, and in this case you can see that we haven't adjusted the gain enough because these poles between 1 and 2 are still between 1 and 2, and they're outside the unit circle, so we would have to crank up the gain to get around inside the unit circle. Let's go ahead and try to move this 0, let's say at 0.1, just to give us sort of something to play with. And now let's adjust the gain. This one might be easier to grab. I'll grab that one and now increase, whoops, didn't want to do quite that. Let me see what I can do now. So now let me grab them and put them inside the unit circle. Now you can see that I do have a stable closed loop system for this PID controller, and I can start to adjust these maybe to a more acceptable location, maybe at 0.7 plus 0.2. And as I'm adjusting that, you can see that I'm influencing the step response. And maybe I can find a sweet spot which is looking about like maybe 0.7 plus and minus j.19 in this case, and that's now a pretty good closed loop pole response if we wanted to leave it at that. And you can see then that I can change this by adjusting poles and zeros. I sort of like that 0 at 0.1 and the other one at 0.9 and adjusting the gain to get me around to 0.7. So now if I do that, what I can try to do is suppose that I now go into Matlab or back into the command window, and suppose that I now say C sub 2 is a transfer function with these two zeros. I had one at minus 0. I'm sorry, at 0.1. I had another one at 0.9. That's now my numerator, which is the convolution. That's how you form the product of two polynomials. And my denominator polynomial in a PID controller will be z squared minus z plus 0, or z times the quantity z minus 1. And that's now my denominator. I'll put in no sample period, and hopefully this is now my PID controller without a gain. So that now I have that, and suppose that I now go in and say, let's go into root locus tool, or let me do another. You could go into root locus tool and say G and C sub 2 and then fiddle around with the gain and maybe the pole and 0. Let me illustrate how we can actually also do this with another couple sets of commands. Let's go ahead and create the loop gain consisting of the original system G and this now PID controller. Here is our loop gain. And this is actually what we want to examine the root locus for. So I could now sketch the root locus for C times G. And that looks consistent with what we would expect. And now let's see if we can find the gain value to get us roughly where we want to be, which was sort of at this plus and minus j.2. That's easiest to find, and we'll just settle for what the real value is for that imaginary piece. So now if I left mouse click at that point, you can see my three closed loop poles are these plus signs, and that was corresponding to a gain of 1.932. So hopefully now if I say, let's call C sub 3 a scaled version of C sub 2, where it's scaled now by 1.9327. This is now my PID controller with the, let's say, with an acceptable gain value. We can now do L gain 2 and say that's G times C. Well, maybe I'll call it L gain 3 to be consistent with C3. So this is G times C3. Here's our loop gain with the PID controller. And for that, we can actually look at computing the closed loop transfer function for that system by using the feedback command. And if we put in 1, that's the feedback path, and gain in the feedback path, and feedback assumes negative unity output feedback. So here is our closed loop system for the PID controlled unstable open loop system. And hopefully now, if we find the poles of that closed loop system, those now are at the values that we expected, basically 0.7 plus and minus j 0.2, and the third pole in the left half plane between 0 and minus 1 at minus 0.323296. And if we wanted to, we could now plot the step response of that closed loop system, which is consistent with what we were seeing in the rltool function or design tool that we were using before. So now that gives us a way to create an acceptable PID controller design by iterating on the movement of these zeros, and we did that using the rltool function, and that now allowed us to come up with a nice controller, PID controller, and in this case I'll just say that our PID controller that we ended up with, since I don't remember the exact value of the gain that we settled with, but you can find that in the notes of Matlab that I will provide with this. But now our PID controller had some gain k bar where we had one of our betas at 0.1, the other beta at 0.9, and if it's a PID controller, we know we have one pole at the origin and the second pole of our PID controller at z equal 1, and that pole at z equal 1 provides us with a way to get zero steady state error due to a constant input. So this is now giving us, which we did in Matlab, this z squared minus z plus 0. There's our three coefficients that we had identified in our denominator polynomial inside the controller's transfer function. That's now going to wrap up our PID controller design approach, and what I would like to do now is go into a strategy where we have the flexibility or the freedom. Now that we've seen the Ragazzini design approach, we've seen the proportional, the PI, the PID, now we might have a little bit more confidence in our ability to select poles and zeros from a generic transfer function. And to get us started, suppose that you're now in an interview and somebody gives you the following. They say, here's a system, G sub 2 of Z, and I would like for you to stabilize that system by the choice of a controller. The objective then is to stabilize G sub 2 with some controller, which we'll call C of Z, and again we're using our conventional unity output feedback configuration with a plant G and a controller C. And what you might do, if this is now in an interview, you might say, well, let me just look at what we have and see what we can do, maybe with a basic controller, where the basic controller now is a gain controller. And in this case, we have a pole of our original system at 2, another pole at 1/2, and we have a 0 at 1. I hope it's clear that in the open loop, this system is unstable because we have a pole at z equal to 2, and in fact, if we now look at the root locus associated with this, meaning we now have a controller that's just a proportional gain, we would have a branch of our root locus that was be fixed between 1 and 2, and the other branch would be going off to minus infinity as we cranked up the gain k. And there's no way that we can stabilize this system with a pure gain controller, and I hope you can see that for a couple of different reasons. If this is now our unit circle, we would want to be stable, both branches to be simultaneously inside that unit circle or inside that yellow highlighted region. Well, you can see that in order to get the pole that starts at 2 even close to the unit circle on the right side at z equal to 1, that would require a very large gain. And in fact, before we even reached that gain, this pole at 1/2 would have quickly zipped through the left side of our unit circle at z equal to -1, and it would be outside the unit circle as we started to approach the unit circle from the right. And even if we made it to the unit circle, that pole would be canceled by that 0, but in fact, even if we had a pole on the unit circle, that's not good because we could then hit that with a constant input and cause the output response to go unbounded. So that having a pole on the unit circle produces an unbounded response due to a bounded input. So we would have not bounded input, bounded output stability if we have any of our poles on the unit circle. In this case, what I would like to say then is with a pure gain controller, we have an unstable closed loop system. Now, I said if we were in an interview, this is maybe what we would talk about with our interviewer, and we would say, okay, we can't stabilize that system with a pure gain controller, but what's possible if we make our controller maybe a little bit more sophisticated? Again, we're not going to change the system at all. It has 2 poles, one inside the unit circle to begin with at 1/2, the other one at z equal to 2, and we have a pole at z equal to 1. What we're trying to do then is eliminate that root locus branch that was living between 1 and 2, or at least allow us some opportunity to not be stuck there for all time. If we were to put a 0 there, what would happen? Well, you might say, oh, that looks like a great idea, but in fact, that would cost you 50 points on a 2-point problem, and we know not to cancel poles or zeros outside the unit circle. But that does not mean that we can't introduce poles and zeros outside the unit circle. Suppose we put a 0 right there. What does that do? Well, now we have this segment, and again, we're stuck between the pole at 2 and that 0, let's say at 1.5. So a 0 introduced between the 1 and the 2 is not going to work. What would happen if we were to introduce a pole? Now we have 2 branches of our root locus, one going to the right, one going to the left. They will meet and break away. And if we were clever, maybe, with our 0 location, we could cancel that, and now we have this circle with the 0 as the center of that circle, the breakaway point being the geometric mean of the two lengths, one length being between 1 and that, let's say, pole at 3/2, and the length from 1 to 2. So we have 1, the square root of 1/2 times 1, or the square root of 1/2, or 1 over the square root of 2 for our radius. We now are coming in here, and that's obviously not drawn accurately, but these two would now be giving rise to a potentially stable closed loop system for the appropriate choice of gain K. So in this case, we actually introduced a controller that now was, let's say, had a pole factor of z minus 3/2. It had a 0 factor that canceled the pole at 1/2, and we would now need to calculate a k bar to maybe put us at the triangle location. But what we're seeing is that an unstable controller pole allowed us now to not have us fixed always between 1 and 2 with a branch of the root locus, and that unstable controller pole is now actually helpful in stabilizing the closed loop system. And if we actually carried that a little bit further, suppose that we now said, you know, this is getting a little bit interesting in terms of this question that you've posed. What if I now look at another possible location for poles and zeros? Again, we'll start with our system that you gave me to begin with. As the interviewer, you gave me this, but now I can sort of anticipate maybe an easier way to design a stabilizing closed loop or controller. So here's my unit circle. Again, you may have to use your imagination to see that that is a unit circle, but that's what it's supposed to be. It was nice when we canceled that, and now suppose that I locate my pole not between 1 and 2, but right at 2, and now my geometric mean calculation between the 0 and those two lengths is pretty easy. It's the square root of 1 times 1, and now my root locus is going to be a circle of radius 1 with center at z equal to 1. So these two poles come off of each other immediately, and they head around, they re-enter right at the origin. One goes to the 0 and the other one goes off to negative infinity. And I hope now you can see that in fact we have the possibility of finding these limiting values of gain that we could use to guide our closed loop pole selection. For example, if we looked at a gain to get us to that particular point, the triangle, that's the minimum gain that we would need. So here, let's say that we have K delta, or K triangle is our minimum value. We could crank up the gain a little bit more and get us to, let's say, right there where they're both right on top of each other. I would say that that might be an easy gain to find. I'll say K easy, because that's actually going to be, if we used our magnitude condition to find an expression or an equation for the gain K, we could evaluate that K expression at z equal to 0, and that would give us the gain to get us to star. And then we could crank up the gain some more and get us all the way out to the z equal minus 1 point, and by that point maybe we are getting close to the 0, the finite 0, at 1. But now this would be our maximum value for the gain k, where now we can look at, if we remind ourselves what we started with, we had a plant, g of z, that was z minus 1 in the numerator. We had z minus 1 half and z minus 2 in the denominator. And our controller, we went ahead and canceled that stable pole at 1 half with a 0 factor, z minus 1 half. We have a gain k bar, and we introduced an unstable pole at z equal to 2 to give us this nice circular shape. And that nice circular shape now allows us to make the following observation. The distance from the origin to that triangle, because that triangle is on the unit circle, I hope it's clear that that length is 1. We know also that this is a pure circle, and the radius of that circle had this geometric mean value of 1. So if we rotate around with that radius, the distance from this 0 center to this triangle is 1. And I hope it's clear that the distance between 0 and 1 is 1. So that's actually an equilateral triangle, all three sides equaling 1, which then says, oh, that's an equiangular triangle, and all the angles now are 60 degrees. And now we have a pretty easy way of finding where that triangle location is to give us our minimum value of gain. And the maximum value of gain is pretty easy to find, and also k star is easy. So let's use those to determine this range and maybe our Goldilocks value for gain in our system. The magnitude condition we can create based on this plant G and controller C, so that now we have the magnitude of our controller, which is k, I'll forget the bar, z minus 1 half over z minus 2, times our plant, which is z minus 1 half. Whoops, not what our plant was. Our plant had a 0 at 1. I just need to scroll down a little bit. We did have a pole at 1 half and another pole that was unstable at 2. And our magnitude condition for the root locus says, or from the closed loop denominator expression, which is 1 plus c of z, g of z, that determines our closed loop poles. We use the magnitude condition because we know that the magnitude of c times g has to equal 1. We can now use that to create this expression for k, which is the magnitude expression. And in fact, we don't have to worry about those two factors. They cancel. And k now being solved for is now z minus 2, two of those, over 1 z minus 1 factor. So that from this, I hope it's clear that if we wanted to find the easy gain value, which was k when z is equal to 0, now I think you can see why I said that's the easy choice for pole locations, and that would give us what kind of a system response. If both of our closed loop poles are at star for this gain, that's going to give us two closed loop poles at the origin, or at z equals 0. If all of our poles are at the origin, we now have a deadbeat response, and that will now be possible with a gain of 4 over 1, or 4. So with a gain of 4, we now have a deadbeat response. Another easy gain calculation would be the maximum gain, which is k when z is equal to -1, or that's now -1 minus 2 squared over -1 minus 1, or this is now 3 squared over 2, which is 9 over 2, or 4.5, which is bigger than 4. So our maximum value is 4.5, and in fact, if we look back at what we had here in this picture, if I draw it a little bit better, you would see that we now had the triangle right there, and there's our origin to the triangle. Here's the triangle to z equal 1, and here is now the 1 there. So here's 1, there's 1, there's 1. This distance, I'm sorry, that angle is 60 degrees because it's an equiangular triangle. So this location is now 1 times the cosine, so our radius is 1. The real part, if we project it down on the horizontal axis, is going to be the hypotenuse times the cosine of 60 degrees. The vertical distance plus j is going to be the radius times sine of 60 degrees. The cosine of 60 is 1/2. Now we can take that squared plus this imaginary component squared, and they, since they're on the unit circle, have to have a magnitude of 1. 1/2 squared is 1/4, and if we squared the square root of 3 over 2, that would give us 3/4, and this is now our location for the triangle in our root locus diagram, which governs or tells us when we would be first entering the unit circle, or that's our minimum value for gain. So in this case, k delta is k min, which is k equaling, or evaluated at z equal to z delta, which is now 1/2 plus j square root of 3 over 2. We can now substitute that in for z, so that we have 1/2 plus j square root of 3 over 2 minus 2. We need 2 of those, and we have 1/2 plus j square root of 3 over 2 minus 1. We had 1 of those. Upstairs we have minus 3/2 plus j square root of 3 over 2. 2 of those lengths, and downstairs we have minus 1/2 plus j square root of 3 over 2. And if we find the magnitude of the numerator and square it, so that will allow us not to worry about the radical, downstairs we have 1/2 squared plus the square root of 3 over 2 squared, and we square root that. But now we have 9/4 upstairs and 3/4. Downstairs we have 1/4 plus 3/4, which ends up being 1, so we can forget the denominator essentially. And now we see that the minimum value of gain, k delta, is actually equal to 3. Meaning we can now have a stable system as long as k, for that choice of pole and 0 in our controller, which had an unstable pole in the controller, as long as we have our k between 3 and 4, we will have a stable system. And it could be that we like our easy choice of having a deadbeat response when k was equal to k star. Or we may want to be between 3 and 4 and have our closed loop poles now somewhere between this triangle and star location on this circle of radius 1 centered at z equal to 1. And we could now play with that using rltool if we wanted to experiment with which particular step response do we like for that choice of controller pole, which is at z equal to 2, and controller 0, which is at z equal to 1/2. If we now look at one more example, the previous example dealt with an unstable system. Suppose now your interviewer says, oh, I assumed you could stabilize an unstable system. What if I give you a system that has a 0 outside the unit circle, or it's a non-minimum phase system? Again, a non-minimum phase system that you may be familiar with is a bicycle. May not have these dynamics, but it does have a 0 that's outside the unit circle in a discrete time representation of that bicycle's dynamics. Here we now have a 0 at 2. We have a pole at 1 and another pole at 0. And I think you can see then that this, like the previous example, we're stuck now with one pole always living between 1 and 2 if we just tried to use a constant gain controller. So with a constant gain controller, we have an unstable system. So we have to do something other than what we have with just a gain. So let's now take out another napkin if we're in an interview and trying to figure out how to stabilize this system. Now it was an unstable system because that pole at 1 is marching off to the non-minimum phase 0 at 2. Now what we want to do is again try to get rid of always having a branch of our root locus between 1 and 2. And if we put a pole here, that's not going to really do anything for us. We're going to continue to have that branch between, let's say, 1.5 and 2 for any gain k of our controller if we had a pole at 3/2. So a pole is maybe not going to work for us, but what if we actually had a 0? Now if we had a 0, we will have a root locus diagram that will eventually terminate at those finite zeros. But we can't just introduce a 0 without a pole, because one 0 factor with no pole factors would give us a non-causal controller. Again, if that's not clear, go ahead and just write down the formula for the transfer function with just a 0 factor. Find what the difference equation is between the error signal and the input to the system and see if that doesn't produce a non-causal response. So we actually have to introduce, in concert with that 0 factor, we also have to introduce a pole. And now with one pole and one 0 factor, we now do have a causal controller. And what we now have is we have this is a branch, or it's actually two branches of our root locus, but that's a segment of the real line segment that belongs to the root locus. And we have this segment of the real line that also belongs to our root locus. So these two poles will approach each other. They will hit and break away, and those two will re-enter between the finite zeros, and we have another third pole or third branch of our root locus starting at the origin and going off to minus infinity. And what we're hoping then is that we can now crank up the gain to some value less than, let's say, these boxes. And so for a tiny gain for this choice of pole and zero, now we introduced another zero outside the unit circle. And for that, we now have stabilized our system by putting a pole inside the unit circle. Our two poles now will approach each other, let's say between 1/2 and 1. They will break away, they will re-enter, and they will come down between the two zeros, and one will eventually go to a 0 at, let's say, 1.5, and the other 0 at 2. But now what we can see, I hope, is that at the triangles, let's say the gain to get us to that triangle, which isn't going to be very big, we're going to be restricted to having our gain less than, let's say, the box value of gain. This K triangle is a stable closed loop system. And so for that plant that we started with, which was G sub 3 of Z minus 2, Z minus 1 times Z in the denominator, our controller that we created, let's just pick some numbers, it really doesn't matter. We had a pole factor, let's say, at 1/2, and we had a zero factor at 1.5, and then we picked the gain K, maybe to be K delta, and now our closed loop system will be stable. So I want you to realize that we can, and it's many times beneficial, to introduce poles and zeros outside the unit circle, but we cannot cancel poles and zeros outside the unit circle. In this last example, we started with a system that had a 0 outside the unit circle, and in fact, to create a stable system, we needed to go ahead and make or introduce another 0 factor that's outside the unit circle. And in order to keep our controller causal, we needed to introduce a pole factor. Now we have the same order for our numerator and denominator in our controller. This is now a causal controller. And it's able to now stabilize that original system that with just a pure gain controller was unable to be stabilized. And that's where I would like to finish then with this transfer function based controller design approach or approaches. We've done the Ragazzini, we've done PID, which you can think of as proportional, PI that gives us this nice steady state error capability, and the PID, which allows us to not only have the nice steady state error because of the integral term, but the derivative term allows us to adjust the transient behavior. And we also now are a little bit more experienced in how we can sprinkle poles and zeros in the z-plane to produce stable systems when a pure gain controller may not, in fact, stabilize those systems. So that's now going to complete our discussion of transfer-based controller design.